Hello, my name is Andres Rubio, taking Physics 2211, and this is my Lab 3, Black Hole and Orbit. So to start off, we're going to split off this lab into two main parts. Part 1 being the black hole, which we're going to analyze the motion of a star orbiting a black hole to derive the mass of said black hole. And Part 2 is going to be the orbit. So we're going to determine the initial velocity needed for a spaceship to orbit both a planet and the planet's moon with observable force from both. And we end off with a final mass of 1.1749 times 10 to the 34 kilograms for the black hole. And then for part 2, we found this is just the initial velocity that I chose, but we ended off with an initial velocity of 2.9 times 10 to the 5th and 2.4 times 10 to the 4th. And the main fundamental physics principles that we will be using are Newton's second law of motion, momentum, and gravitational force. As I said previously, the main fundamental physics principles that we'll be using are Newton's second law of motion and gravitational force, and how momentum plays a role in both of those. So we see here that the net force can be derived as the change in momentum over time, and we see the momentum is mass times velocity. And momentum can be split up into two different parts, its perpendicular and parallel form. So we can then turn that into both a perpendicular and parallel component for F net that we can use in the gravitational force formula to derive a mass, which will be our black hole. So we'll be able to derive the mass of the black hole using the formula for gravitational force. And now for part 1, our black hole. And now for our initial conditions and system properties, we see the first 4 lines are just constants: the gravitational constant, the mass of the star, how many seconds are in a year, delta t, and t. And then at the bottom we have a loop that holds our x and y components for our velocity. And then at the very bottom you can see my seed, which differentiates my results from others. And now for the second part of our computational model, we see our calculation loop, in which we basically continuously update our velocity, and then we update momentum based off that, and then we update our change in momentum and velocity based off of the time, and then we eventually get our force. And then with our force, we split it up into perpendicular and parallel, and then based off of that, we are able to get our mass of our black hole at the very bottom. And for our results, we see that after the star has made a full loop around the black hole, we see the perpendicular and parallel components and the net force. We see that the mass that we calculated on the bottom left is, the average mass is 1.1749 times 10 to the 34. And we clearly see in the bottom left that that seems to line up. And now we have part 2, orbit. Okay, now these are the initial conditions that we started off with, pretty similar to part 1, but now we include the moon velocity and moon speed, because this consists of a moon revolving around a planet and how our ship interacts with those two forces. And then at the very bottom we see the ship that is moving from the moon to the planet has both an x and y component that we will just be figuring out through trial and error. And this is what I ended up with, 29,000, and just the moon speed, which is around 2,400. And now this is our calculation loop, and as you can see here, we do calculate how the planet is relative to the moon and the ship is relative to the moon. So we calculate the position and the force based off of that position. And then at the bottom we see that we also do the same thing but relative to the ship. So planet to ship and moon to ship, we calculate both the position and forces. And we see that we increment the velocity and position at the very bottom as well. And now for our result, we see that the trail of the ship is basically the magenta lines, and we see that the ship has been interacted with by the planet, but you can also see that the moon played a role in basically pivoting the orbit that it had. As you can see, it like skews to the right, so that's the influence that the moon has on the ship's orbit. And now for conclusion. Okay, and for possible errors, first up we have human error. I could have maybe picked a better x and y component to the ship's velocity. That's all there is to it. And simulation. We aren't accounting for every single force, but we are accounting for the main forces in the simulation, but in reality it could differ wildly. And for the what if, for our first what if, what does it mean? How are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? And the main difference is that although like they equal the same thing, we derive them differently. So the net force is basically each force on the system acting together, but momentum is just a change of velocity times the mass. So that's all there is to it. And then what if the system had a black hole, a star, a planet, and a moon? Essentially, that would just be more forces interacting with each other, and for the dominant forces, it would be black hole to star, and then star to planet, and then the moon would be affected by all of those. Thank you. Have a good day.